Alright, so all we're doing, real quick in our notes here for a little bit. What's the last thing we had? Dot structures?
Yeah.
Are you going to edit this so you don't have all this beginning?
What?
Kimber.
What are you talking about?
Is
YouTube
it
channel.
Edit what? You just started.
Yeah, but like,
Yeah,
all this
but
copy
like-
stuff.
It's been for like 20
That must
seconds.
be really
Are you
annoying.
going to edit it out?
Ionic character, write it down. How do we find ionic character? We subtract electronegativities. If we take NaF versus, let's say, AlF3, I want to know which one has greater ionic character. I look up their electronegativities. So, somebody look up Na for me on table S. What is the electronegativity of Na? Someone look up F, someone look up Al. Na is 0.9. F is 4.0. What's Al? I forget already.
1.6.
1.6. Okay. What's 4 minus 0.9?
3.1.
3.1. What's 4 minus 1.6? 2.4. Which one is more better?
3.1.
This has a greater ionic character. It means it is a better ionic bond. It's stronger. And the reason for that is if this is really, really low electronegativity, Na forms a very good +1. It's a really strong positive because it really doesn't want electrons. F is the highest electronegativity, so it forms a really strong -1. So those two are really, really, really attracted, and this is how we word that. Greater ionic character, meaning it has better ionic properties than, let's say, that, AlF3. And one thing I did want to mention with this, you don't have to write this, but when Na loses that electron, so let's say, actually, can I erase this?
Yeah.
I know I'm going quick, but stay with me. So the moral of the story there, subtract the electronegativities. The bigger the difference, the more ionic it is. Now, if you take Na, you do not have to write, just watch. Let's say Na is this big and F is this big before they bond. Hey, Adriana. So you can sit right behind that if you want to.
I don't think you can even see.
Yeah, it's up to you.
Right?
All set? All right. Okay, so back to this. So before they bond, do you need to pass or anything?
No.
Okay. Before they bond, they're this big. Now, after they bond, Na gives an electron to fluorine, and as a result, it becomes Na plus and F minus. What happens to that atom?
Small.
Right. So Na plus gets smaller and it becomes positive. What about this one?
Bigger?
It gets bigger because now it's negative. Now these two are attracted to each other, and that's a good thing. The smaller this ion is, actually the closer it can get to that. So when they actually come together and they touch, let's say, it's not really exactly that way, but when they get close together, that's a better bond. The analogy I can use, I don't have another basketball, but if I took two basketballs and put them next to each other,
Yes, you do right
okay?
there. That little one.
Well, okay, that's a good example for this, but if I took another basketball and put it next to this, the center of this, just let me finish, the center of this ball and the center of the other ball would be pretty far apart. But if I took a little one and a big one and put them together, the center of this one is closer to the center of this one. So if I have two little ping pong balls, let's say, put them together, the centers are very close together. Does that make sense?
Yeah.
Now, what does that have to do with bonding? The way it actually works, when these things bond, besides the fact it's opposite charges, the way it really works is you have the nucleus here attracted to the electrons of that one, and the nucleus here is attracted to the electrons of that one. So they're pulling each other close because they're attracted to the opposite electrons. So the closer those nuclei can get, the closer they are to the other electrons. So when this gets smaller, that's a good thing. So if you take a metal that's bigger, an ion that's bigger than Na plus, it won't bond as strong to the F minus. I kind of just went way above Regents Chem there, but I think it's important for you to know that. So that's important to understand. This gets smaller, that gets bigger, and how that affects the bonding. All right. So anyways, that's ionic character. Real quick here, we'll get a couple properties down. And then that'll be it. Don't forget that bookwork. So Adriana, that bookwork is due Monday. So ionic properties, here we go. And we're learning about this in lab. So we learned that they have high melting points. So I'm just going to write high MP and high BP. High melting points, high boiling points. Takes a lot of energy to melt them. And that, I guess we can write, is strong, that word over there, electrostatic interaction. Electrostatic interaction. And that is the positive negative. So that's your positive ion, positive, negative, and we'll just put dotted line, means they're attracted. So when you have in that ionic crystal, it's really strong because of that opposite attraction. Okay, so that's high melting, high boiling. Okay. High melting, high boiling. What else did we say?
Crystal, like.
All right, so property, it forms
Rock. Oh yeah, that too.
forms crystalline structure. And it's hard, right? They're hard, but can break. And I actually want to show that picture here. I don't know if I'm gonna, we'll have to finish this
Probably won't.
Tuesday, but draw this. Oh, no, I don't want to show you anything except for this. So give me a little drawing. This is what it kind of looks like in the crystal. Remember, each layer is going to be opposite the one above it. So that shows strong attraction. That's bad. Shows strong attraction because opposites are touching. But if you hit, let's say, the bottom row with some force, like the world's smallest hammer, okay? You hit this entire row is going to shift, and now you're going to have positives and negatives lined up, so they will repel each other. So they are hard, but they break, because I can erase this. If you want to rewrite the whole thing, you can, but if I hit that, basically what happens here is the charges now line up. So if the charges line up, this right here is going to break off. So they're going to break off because they're going to repel similar charges. That's why ionic crystals will break. So we got a little bit done. Bell's going to ring. Well, there's no bell, but it would ring very soon. So you can wrap it up. What's the one more, real quick here, you can pack it up, but what's the one more property we're going to write down we learned in lab today?
Solubility. No, conductivity.
Right, ionics conduct in water, and that's what we're going to write on Tuesday. So we'll talk more on Tuesday about that. And that's it.
Can we just leave?
Yeah, I guess.
Back.
Leave that in.